Hi, I'll start with a short recap of what we went over last week before we jump into correlations and regressions, which are our topic for this week. So we're still in the counting beans section of the unit. So we were talking about probability and how we sample, and we started talking about all sorts of statistical tests we're doing, and now we're starting to look at correlations and time series. Analysis will come next. So yeah, make this a bit smaller. So we start off with the elements of a statistical test. So for that we need distribution. So we have test variables, and they distribute along a probability density function. Within those we have all sorts of moments like the mean and the standard deviation. And these two parameters determine the confidence interval, our confidence around the mean of the population, whether we know if this mean belongs to this population, or maybe it's from another population that is not shared. So that was our confidence interval, and when we applied that, the probability of getting a value outside the confidence interval, the p-value, the probability value, we had regions where the null hypothesis was true and where the null hypothesis can be rejected. So that was what we spoke about. We applied that philosophy in a few kind of tests that we tried out. We spoke about one sample t-test, paired t-tests. That was comparing two populations, two sample t-tests. Again, two populations, but not paired. And then we spoke about comparing more than two groups. So we have analysis of variance, or what we call ANOVAs for short. And those were all to do with variables that are continuous and normally distributed. But we also spoke about measuring things that are not continuous, the things that are categorical, like colors, like handedness. So the student t-test is the t for t-test. The t, the statistic that we're using to describe a population, is a function of the effect size, so the difference between the means between the populations, how variable each population is, so the standard deviation. So if I think about it together, that's kind of the signal to noise ratio. The bigger it is, the bigger the t. And I multiply that by the population size, how many samples I've got. Okay, so my population of samples. And here I have, as the t gets larger, I'm pushing towards the right side of that distribution, right? As t gets very large, it becomes less likely that it is from a population of t's that would arise from a null hypothesis being correct of no difference in means. So of course, if they have zero difference in means, my t is zero. Okay, so as this mean gets bigger, t gets bigger. Okay, and then we said, okay, what happens if we have more than two groups that we want to compare? And we saw that in the soils, we had 3 different sites we wanted to compare. We can think about looking at different, I think in the prac we were looking at conglomerates with different rocks, pebble sizes or something like that. So we have more than one group we're trying to compare. So we use a test called an analysis of variance, or when you use R, it's AOV. And then we spoke about comparing categorical data. So for example, handedness in class versus handedness in the general population. So if we have 32 students in the class and 4 of them are left-handed and 28, and we have an expected value, which is what the handedness in the general population is, which is about 10% of the people are left-handed. And I place that into this chi-square, sometimes you see it written as c-square, index, and of course that the chi-square has its own distribution, and I can work out whether my chi-square, the one I calculated from my data, is different enough from the null hypothesis chi-square. And lastly, we spoke about non-parametric tests, where we actually don't have a distribution to compare to. And a lot of this falls back to using ranks, and these are much weaker tests. We don't use them as frequently. We always try to aim for a normally distributed data set. We actually did not really have a chat about this. There's just not enough time for everything, right? So moving on to the new content is regression and correlation. Now the two are not the same thing.